exponential number of steps, this could be plausible because there's an exponential number of matchings. But we'll show that this is not the case. And the third thing we need to do is that, well, to show that this actually put set of hospitals on the left. So the big dots on the left, there's a set of doctors on the right, so the big dots on the right. There's the same number of hospitals as doctors. Each hospital wants to employ exactly one new doctor. The hospitals have a preference over all the doctors. So with each hospital, on the left of the hospital, we see the preference list of this hospital over all the doctors, and the same on the right. So the leftmost is the most preferred doctor for each hospital. Same, the leftmost hospital that's being displayed on the list on the right is the most preferred hospital of each doctor. And so we saw how this, so what we wanted to achieve is we wanted to match exactly one doctor to each hospital, such that we don't have a so-called blocking pair. So a blocking pair is a hospital and a doctor that would rather be matched to each other than to the solution that we provide. Then to whomever they are matched in the solution that we provide. So they don't want to leave our system and run off with each other. So how did this algorithm work? Well, the hospitals proposed. So each hospital proposes to a doctor, and the hospitals take turns. So the hospital proposes to them, but then the doctors keep getting better offers. At some point we stop. But like the hospital doesn't have doctor yet. So this means that the hospital has actually proposed to every single doctor and has been rejected by every single doctor. So this means that all of these n doctors have a better job already. Because if they don't have a job, they accept. If they have a worse job, they also accept. So they must have a better job, either of them. But where do they work? Yeah. Oh well, okay.
So I think what questions are to them?
Bro, what's going on?
But so if we look at what a hospital does, so a hospital makes an offer to their most preferred candidate. Maybe they lose this candidate at some point, which means that if they lose this candidate, it means that this candidate has found a better job. So they would not be rather matched to this hospital. And then they go on to offering a job to the second most preferred candidate, etc. But everybody who has left this hospital has found a better job, and they would not be rather matched to this hospital. So basically this hospital gets their best possible candidate. And so this hospital doesn't want to change. So that means that there cannot be such a blocking pair because hospitals don't want to change whoever they are. Well, they might want to change, but they know that, well, if they try to make an offer to another more preferred doctor, the doctor will say no. So we can formally prove this by contradiction. So assume that the matching that's produced is not stable. Therefore, there are two pairs, HD and H'(D), such that H and D prime would rather be matched to each other than to whoever they got in our matching. Okay. So since this hospital H prefers D prime over their current match D, it must have already made an offer to D prime before offering the job to D. But this Dr. D prime basically at some point found a better hospital. So basically, D prime must at some point have rejected this hospital immediately because they already had a better job when they got the offer, or they must have left the hospital because they were previously at this hospital, but then afterwards got a better job. So in both cases, D prime is now at a hospital that D prime prefers over H. And this is a contradiction, and this completes our proof. Okay. Are there any questions about the stable matching algorithm that we've seen here? And I must say this is still a very active area of research because there's lots of variations that you could look at. One common variation is where there are hospitals that are couples, and couples want to work at the same hospital or at close location, or hospitals that are close in location. You could have other constraints, like you could have diversity constraints for the hospitals. You could have constraints about specialities. Some doctors, it shouldn't be the case that the hospital only hires doctors in one specialty. They should also broaden their people. And then, besides hospitals and doctors, there's all kinds of other matching settings that we can envision. Some people from the NSW, including me, have worked on the problem where we match refugee families to concepts. So in the model that we try to do. Okay, the next thing. Is actually puzzles. So in general, we're not going to see solutions to the puzzles. Let's have a brief look at this one, and I can give you some hints, but so in general, we're not going to see solutions. So Tom and his wife Mary went to a party where 9 more couples were present. So in total, we have 20 people at the party, and there are 10 couples. Not everybody knows everybody else, so everybody who did not know each other introduced themselves and shook hands. People who already knew each other from before did not shake hands, and later that evening Tom got bored, so he walked around and asked all of the guests, including his wife, how many hands they had shaken that evening. And he actually received 19 different answers. And now, based on this information, it's our task to find out how many hands did Mary shake, how many hands did Tom shake.
Bruh, what?
So it looks like we're being given very little information, and we have to come up, we have to find out these
Looks like we've been given no information. We've got 19 different answers. What does that mean? Got 19 different answers. 9 more couples were present. How many hands did Mary? How do you solve this? So people who did not know each other introduced themselves and shook hands. Bro, what? Should I try to solve it? I can try, I guess. Don't think I will be able to. How many hands they had shaken that evening? Got 19 different answers. Ask all other guests. Oh yeah, I guess there were 19. Got 19 different answers. Does that mean it has to be? So there were 19 people. Since there were 19 people and there were 19 different answers, does that mean one person knew all of them? So 1. So can one person shake 18 people? No, that's impossible, right? Because you can't shake your own hand. So it was actually 0. Got bored, so I walked around and asked all other guests how many hands did Mary shake? So Mary shook at least. Well, 9 more couples, not everyone else. Including his wife, how many hands they had shaken that evening? Got 19 different answers. Isn't it impossible to get 0? Got 19 different answers. Oh wait, there were 10 couples. Okay. So if there were 10 couples, you can have a max of 20 different answers, I guess. This is so abstract. What's going on? But got 19. But yeah, 19 different answers. He didn't ask himself, right? Person 1 could have shook in 19 people's hands. Is it possible to shake 0 hands? Yeah, it is. Different answers. These are the 19 different answers. How many hands did Mary shake? How can you just ask that out of nowhere? How many hands did Mary shake? How many hands did Tom shake? Got 19 different answers. What? There's no way I'm solving that.
This information about Mary and Tom. So, like we really need to use all the information you're given in order to make any progress at all. I think one of the big things is that so Tom got 19 different answers. So if we maybe put our people into a graph, we have a vertex for every person at a party, and now maybe we draw an edge between 2 vertices if those persons shook hands. So we'll see that, well, the number of people that they shook hands with is the degree of the vertex in this graph. And so we have 19 different vertex degrees in a graph on 20 vertices. And we don't know anything about Tom, right? No. We don't know Tom's degree. We know the degrees of everybody else. So one of these vertices is Tom. The other 19 vertices have all different degrees. So basically all the degrees from, none of them has to be 20, because there's only 19 vertices. 19 order vertices that they could introduce themselves to. And there's one thing that we need to do is that, well, why are we being told that these are couples? That's probably the only reason why we are being told that these are couples is because, well, we assume that inside a couple they know each other already. So
Yeah.
they will not be shaking hands with their partner.
So you can't have
So basically everybody has degree at most 18. So then you can find out, okay, so there must be somebody with degree 0, somebody with degree 1, etc., until degree 18. And, well, slowly working out, well, if you have a degree 0, maybe you can eliminate them. If you have somebody with degree 18, well, we know more or less who they are. Well, they are basically, they have matched to everybody except to their partner. So we kind of build up our knowledge about this graph, how it looks like, and then in the very end, once we have reason about all the vertices, at the end we find out something about Tom and his wife.
Okay, let me draw that. 19 dots. Come on, G. I ain't drawing that. It's friggin' 20 dots, isn't it? Whatever. Five, 6, 7, 8, 9, 10. 16, 17, 18, 19, 20. Okay, so there is one person that knows a 0. There's one. But you can't point to them. Because if you know them, then they know you, right? Two, and this guy goes here. This is a degree of 2. This has a degree of 3. So 1, 2. It'll be like that. 3. Need a bigger circle, I reckon. Yeah, let me just copy and paste. Nobody, this guy knows one person, this guy knows 2 people, this guy knows 3 people, so this guy and knows 4 people, so you already have that. So 1, 2, 3, 4. That's 5 people. This guy has 6 people. So 1, 2. 4, 5, 6. Is it something like that? Wait. 1, 2. Let's get rid of the 6. One, 2, 3, 4. That's 5. Bro, why can't I draw a straight line? Six, it's already 1, 2, 3. Something like that. I didn't see a pattern. Like, I see the pattern, but like, is it useful? 7. Already got 1. Two. 3. What about 8? 8's already got 1, 2, 3, 4, 5, 6, 7, 8. Huh? That doesn't give me any information though, I don't think so. It doesn't, it really doesn't.
Why do we have tolerance? Well, because it's a fun way to practice problems and to resolve it. But this is not directly related to course content, but it gives you kind of brain teasers on the way. Okay. Our main topic for today is the preliminaries. So we're going through some of the more advanced concepts that you probably know already, but it's basically meant to bring everybody up to speed. So we're going to see a little bit about complexity as asymptotic notation. I'll tell you what you need to know about logarithms, which data structures you're expected to know, binary search, and then we have quite a large section of sorting, and then some basic terminology about graphs. And of course, you need to know graphs because you want to solve puzzles. Okay, so the first thing is about if you want to analyze the running times of algorithms, well, usually we take a high-level view. We don't care so much about the actual processor that the algorithm runs on. What's the exact instruction set of this processor? What parallelism it makes? It's more about roughly how many steps does the algorithm take. And you probably know already some things like bubble sort takes maybe quadratic amount of time, and heap sort is faster. You probably know these things already. And that linear search is slower than binary search. So we want to make these things a bit more precise. So like we're going to say things like, well, bubble sort has a quadratic running time, something like this. Or maybe we're even more precise and say that, well, in the worst case, the running time, there are actually instances that take this amount of time. Right? It's not just an upper bound on the worst case running time, it's actually also a lower bound on the worst case running time. And so then we can say that well, the worst case running time for bubble sort is theta of n squared, which means that it's both upper bounded and lower bounded by n squared, or n squared. And then maybe we can say something like a heap sort has worst case running time, order n log n. So asymptotically, it will not go faster than n log n. Okay. So I already mentioned worst case running times. You could also study best case running times, which means, well, you just look at the instances where the algorithm is really fast. And, well, I think it's much more useful to look at the worst case running time. There does not need to be made that maybe the average case running time is also important to look at with this book. If you run your algorithm many, many times, then maybe the worst case is more important than the average case. But the best case is certainly something that we do hardly ever discuss. So we'll be focusing mostly on the worst case. For the average case, it's actually often quite difficult to analyze. But it has its merits as well. It needs some more advanced techniques. Yeah, so this talks about the average case performance. Yes, so for these we need probabilistic methods, and it's really beyond the scope of the course, so we will be mostly talking about the worst case running time. And so usually when we say the running time of an algorithm, we actually mean the worst case running time. Okay, so we need some way to compare the running times of two algorithms. So one way you could do it is that, so if f of n tells you precisely how many instructions your first algorithm takes, and g of n tells you precisely how many instructions the second algorithm takes, you could compare the two functions on some, for some value of n, right? But this is not general enough because, well, we don't really care about instances of size exactly 100. We need to make more generalized statements. And it might be the case that, well, for n equals 100, the first algorithm takes actually more instructions than the second algorithm, but then later on, when n becomes bigger and bigger, actually the second or the first algorithm might outperform. So focusing on one particular value for n does not give us enough information. So we want to say something that for large n, one algorithm is better than the other one. So we are more interested about how these algorithms scale. So we'll talk about the asymptotic running time analysis. So one example here is if the size of the input doubles, the function could approximately double as well. And this is the case for linear functions, right? Function which quadruples every time when we increase n will eventually exceed a function that only doubles, right? And this is regardless on the values for small inputs. So we're going to look at the asymptotic way of course. So we could have one function that starts off like this, goes up very quickly, and another one maybe that for small values of n, so let's say this is n, and this is our value of this function, f of n. So this linear function here is in the long run better than this function here, although that function starts off smaller, but then for large n, it really exceeds the previous function by a lot. Okay, so the first thing is that so we use this big O notation, which basically means that we look at large n and we ignore constant values. So we'll say that f of n is order g of n if for large enough n, f of n is at most a constant multiple of g of n. So we only look at large n and we ignore constant values. That's basically what it means. You could make this formal, like you could say, okay, f of n is order g of n if so there exists some value for n, let's call it n0, such that for all n at least this value, and also there exists a constant c, so f of n is at most c times g of n. But basically the English statement is sufficient to express it. Okay, so the big O notation is useful to give us upper bounds on the worst case running time of an algorithm, or the average case running time. But it's always an upper bound on this running time. Right? And usually we're happy with just upper bounding the running time for our algorithm, but you could be more precise. You could also ask, well, are there instances where your algorithm really needs this much time? Okay, let's look at a few examples first. So let's say f of n is 100 times n, then we say that f of n is order n. We also say that the function is linear. Because the reason is that for large n, or actually for all n, f of n is at most a constant, which is 100 in this case, times this function, which is g of n. And we can make the same statement actually for this function, where we can also say that f of n it is both order n squared, but it's also order n. Why is it order n? Well, you can say that for n large enough, so for n large enough, f of n is at most some constant multiple of, let's use the multiple tree, some constant multiple of n. And we said that this happens for n large enough. So you can see that this statement here, even though it's not true for all n, if we make n larger and larger, at some point it becomes true. Right? Then it stays true. So for n large enough, this statement here is true. Okay, the third example is with f of n is 0.001 times n cubed. We cannot say that f of n is order n squared, because, well, if we try to do this, if we say that, okay, 0.001 n cubed is at most, let's take a huge constant, 1000 times n squared, then, well, for large values of n, this stops being true, so we cannot say this. So this is not true for all time. But we can of course say that it's order and truth. Okay, some examples of algorithms that have some given running times. If we have a binary tree with height h, what does that mean? That when we have a tree, maybe have some values associated with the nodes, smaller ones on the left, maybe 5 here, and larger ones on the right, 20 here. So whenever we go left, we have a value that's smaller. Whenever we go to the right, we have a value that's larger. Oops, kind of 6 here, sorry. Negative 16. So okay, the height of the search of this binary tree is, we'll call it 2. So inserting new integer in this tree will take a time proportional to the height of the tree. Okay, what is insertion sort? Well, it's you take a sorted list and you keep inserting one element at a time in the appropriate place. In worst case, this takes order and square time, but order and inverse time. Maybe the list is already sorted. And these statements are true regardless on the details of how we implement the algorithm. It doesn't depend on the programming language that you use or the processor that's being run on. Both of these issues are important. It's important which, let's say, programming language you use, especially maybe if you join some programming competitions. I had a situation where one of the students preferred Java as a programming language, and in the competition, it actually took a lot of time to start up the virtual machine for Java, and so the student lost a lot of time because of this. Okay.
Java's a trash language.
And so in the figure notation, the definition says that we only care about large events. So this is kind of also a limitation of this figure notation, because well, sometimes in some very curious cases, it could be the case that well, n has to be so large that actually we don't care about these instances that are so large because we know that we cannot solve them on reasonable hardware. So it could be the case that when n becomes maybe millions, we have no hope of solving the problem at all, but asymptotically, maybe we only get a better asymptotic running time performance if n is really this large. But officially in the big O notation, we only care about, well, one function eventually at some point exceeding 0. So this makes the point about these very large numbers. So this asymptotic analysis is one tool. It might not be the only one, so if you care about small instances, maybe there's other tools that you need. The big O notation only gives us information about, well, it only gives us an upper bound on the running time, but it doesn't give us, you could think about a lower bound on the worst case running time, right? So you have your worst case running time, that's some function that you want to maybe get some information on. You can upper bound this worst case running time and you can lower bound it. And so this omega notation is a way to lower bound functions.
Omega notation is the lower bound. Okay. Might need to write that somewhere in soon. where's the answer to this friggin' puzzle? What a troll! Wait, what? Is that lecture 2? It is. Can I just search for it? a theta here, but we're looking for an omega. Is that theta? Is that theta? Can't tell the difference. You. Oh. What's epsilon? Yeah, I don't know what is what. Oh, how do we do capital omega? Do I put a capital O? Wow. Does that look the same? Is at least the constant or scale at least as well as is at most. This is at least. Growth rate of the function is no less than. Okay. I guess that makes sense. Bro, what the frick? Challenge. You know, big data notation. f of n equals R of g of n. So the best and the worst case is the same? Is that what it's saying? Fn and Gn are said to have the same asymptotic graph. Okay. As well. The formal algorithm is as fast as the ladder. I think that makes sense. Like, you don't need to write it down. A and B less greater than 0, A doesn't equal 1, let n equal. If A. Yeah, okay. Properties, A, yeah. Just some typical log laws. Change of base rule, yeah. That's just high school math, isn't it? The denominator is constant with respect to x factorial. Okay. Therefore, a log a n is exactly equal to log b of n. Typically write log n suppressing the base. Log a. A question or something? What is... How did I forget? It's frac. What? I was right. Oh, but it's two different brackets. Okay. get back.
And it's basically the same spirit. So we say that f of n is big omega of g of n if for large enough n, f of n is at least a constant multiple of g of n. So then we say that g of n is an asymptotic lower bound for f of n. Okay, so for example, if we have f of n equals 5 times n squared plus 7, we can say that f of n is order n squared. We can also say that f of n is big omega of n squared. And actually, if we put these two together, there's a new notation. If f of n is both order and omega of n squared, then we can say it's a theta of n squared. So I gave some formal definition of the big O notation. Similarly, you can formally define the big omega notation, and you can find these formal definitions in our textbooks. So this big theta notation, the function is both big O of g of n and big omega of g of n, then we say it's big theta of g of n. So asymptotically, we say that these have the same asymptotic course. Okay, the question is, so we've previously seen statements such as bubble sort once in order n squared time in the worst case. Should these statements be written using big theta instead of big omega? They can, yeah. So both statements would be true. So we can say bubble sort once in order n squared time, and we can also say bubble sort once in big theta of n squared time. And if we want to be precise about whether we mean the average case running time or the worst case running time, we add in worst case. The one statement is just more precise than the other one. The first one says, well, the worst case running time is asymptotically at most n squared. The other one says it is asymptotically exactly n squared. Okay? So the big theta notation gives us slightly more information. So usually we are not happy to upper bound the running time because we want to give some guarantees that the algorithm is no worse than something, and for this the upper bound is sufficient. Okay, there's a couple of properties of our asymptotic notations. So let's say that you have an algorithm that actually first runs some algorithm and then runs a different algorithm. So our algorithm first calls an algorithm with running time f1, and then calls an algorithm with running time f2. So in total, the running time of our algorithm is f1 plus f2. So if we have an upper bound for both of these algorithms that are being called by our algorithm, then we get an upper bound for our algorithm by just taking order of the sum of g1 and g2. So let's say, I don't know, our algorithm calls an algorithm with running time order n, and then it calls another algorithm with running time order n squared. So then running time of our algorithm is order n plus order n squared. Would we leave it at this, or would we simplify this expression? Order n plus n squared. Okay. So how should we rewrite this?
Then n plus n squared just n plus n squared?
Order of n squared.
Oh.
So the dominant term is the most important.
Forgot.
So you can see that, well, we can prove it, right? So if you have, so what does order n and order n squared mean? It means that, well, the real running time is, at most, some constant times n plus, so it's c1 times n plus some other constant times n squared for large n. And this is at most, so for large n, this is at most c1 plus c2 times n squared, where basically I just replaced the n here by something larger, so I turned it into n squared. But this is at most some constant times n squared. So that's why we can also just take the max of g1 and g2. Instead of having a plus sign, we can take the max of these two, and then we get a simple expression of the runtime. The same holds for the big omega and big theta notation, where we also have this sum form. So this means that we can only focus on the dominant terms, which means, well, if you have polynomial running times, this means that, well, we focus on the polynomial with the larger exponential. Okay, so this happens when we run some algorithm.
Polynomial runtime.
Before we take our break, let's also look at the product property. So now maybe we have a loop that takes g one time, and inside the loop we call something that takes g two time. Then we multiply the two one times, right? So if we have f1 and f2 that are order g1 and order g2 respectively, then f1 times f2 is order g1 times g2. And same again is true when the big O is replaced by the big omega or big theta. And this is especially useful for like a loop with something else inside. Okay, let's take our break and then see logarithms in 10 minutes. Okay.
Oh, what? I'm not charging. Boy, you got me hooked into something.
Okay, let's continue. So the next section is about logarithms. What do logarithms have to do with algorithms, right? So especially for next week in the divide and conquer lecture, we need some logarithms to analyze our algorithms because when you see some sorting algorithms, for example, have running times that are order n log n, and so this is true for other kinds of divide and conquer algorithms. So, and basically, these slides just contain the basic properties of logarithms that you need. So the definition of logarithms, well, we have a and b greater than 0, a is different from 1, then we say that n is equal to log base a of b if h power n is equal to b. So that's the definition. So basically, if we start from this, and then basically get rid of the base, just want to reason about the exponents, then on the right hand side, let's take the log base a. So I guess directly from the definition, we see that a log a of n is equal to n. And then if we take log of m times n, this is log of m plus log of n, and if we have log of n to the power k.
Right, just
then
reading
it's
the
same as k
slides.
times log of that. So you can think of it's the same as link time. Yeah. Let's start with hash tables. What's a hash table? Well, first of all, the objects that we store in our table, they have you need to be able to apply a hash function to them. And say a hash function gives us some value, and basically that's the location in the hash table where we want to store this item or object. And basically a hash table will be a big array. A new object arrives, we compute its hash value. Let's say the hash value of this object gives us this index, so basically we want to store it in this location in the table. Okay, so it could be the case that we start filling our table, and then some new object arrives that has the same hash value. So in that case, we talk about collision, and so there's ways to deal with such collisions. Could be the case, for example, that when instead of adding our object directly into the table, maybe we start a linked list where we store the first object with the hash value, then follow for the second one as well. The main thing is that in expectation, you can assume that these linked lists are constant size. If they're constant size, then maybe there's ways to increase the size of our table and still store everything with a constant number of columns. In the worst case, well, everything has the same hash value, and so this is one of the data structures where we do care about expected running times. So the expected running times for our operations are searching, updating, inserting, and deleting, all in constant time. In the worst case, while searching, we have linear time because all the objects have the same hash value, so we basically have to search in a linked list or some other data structure that helps us to resolve the collisions. Updating a value has in the worst case or n running time, and inserting and deleting also for that. But in practice, I guess these constant running times are what we see most often. It could be the case that you use a very poor hash function, in which case maybe these worst case running times are relevant, but mostly we'll see constant time operations. And so you could think about, well, what if I just keep adding stuff into my hash table? At some point there must be lots of collisions, right? But then there's mechanisms to basically increase the size of the array, recompute the hash values that amortized. This will still not take too much time. Another data structure that's useful and quite simple is binary search trees. So here, well, we basically have keys that you can compare, and we store the objects. Well,
no tries in here as well.
If we have a key, so let's say that the root of our binary tree has some value, which is the value of the key. So if the key that we want to search is lower than v, then if the object exists in our binary search tree, then it must be in the left subtree. If it's larger than this v, then this key for this object must be in the right subtree. And this is true recursively, so this is true when we continue at the trigger as well. So that each node's key is greater than all keys in its left subtree and less than all keys in the right subtree. And we already saw that the height of such a binary search tree is important because when we search for an object, then basically we might need to traverse our binary search tree starting from the root and then going left or right. But basically, the number of things that we traverse is proportional to the height of this tree. Inserting and deleting also
just 2, 5, 2, 1 stuff.
Okay. Since the height of the tree is so important, well, it could be the case that we are completely unlucky, right? So we start with, we add some object into our binary search tree, maybe plus value 10, and then we add an object with value 9, and then an object with value 8, one with value 7, then one with value 6. So each time we insert something, we increase the height of the tree, which is not very nice because, well, all the operations have running times that are proportional to the height of the tree, and so all of the operations will be slow. But like AVL trees and black trees actually are used to rearrange the tree so that it never becomes too big in height. So, for example, here we could take these two nodes and attach them over here, and make H a new root of this tree, so we can keep the height relatively low by these node mechanisms. We're not going into details of those. There's, I think, AVL trees, wet black trees are detailed in Common Library and Steinbook. But here in this course, it's sufficient if you say we use a self-balancing binary search tree, and then basically what we can assume is that well, in these self-balancing search trees, we have that the height is logarithmic in the number of objects that are inside the tree. This is again a tree-like data structure, binary heaps, but it's different in that well, basically the top elements are towards the root of the tree. So basically the largest, especially if you talk about a max heap, then we have the largest items towards the root of the tree. So maybe we have something like this, where the largest element is always the root. And then if we look at, well, the parent-child relationship, then the parent is always at least as large as the child. So that I have the node 8 down here, which is basically farther down the tree than node 7, but we really only care about these parent-child relationships. So the property that needs to hold is that the parent always has greater value than the child. The operations that we can do here is building a heap from scratch, insert it by adding an element to the heap in order and time, finding the maximum. That's easy, just the root is maximum. Deleting the maximum. Deleting the maximum is interesting because the other thing that we care about is that this is a complete binary tree, which basically means that we fill it from left to right at each level. So if I was to insert another element, well, my tree would have this shape. If I would insert another element, it would have this shape, and then I continue at the next level, right? This, and well, having this nice shape is interesting because it allows us to store a heap inside just no way. And indexing is also easy. Okay, so we can delete the maximum in order of n time, which basically means we delete the last thing here and swap these two. So we swap these two, and then.
I know how heaps work. Why are we learning this?
Once the middle value is equal to x, then we found x. Otherwise, we recurse either on the left or on the right side. The worst case complexity of this is order log n, because well, at each step that we, or after each comparison, we can focus on a subarray that was half the size, and we can halve the array at most log n times. In addition to sorting, we can do some slightly more general problems. We could, for example, find the smallest index I, such that a of I, the array at position I, is at least x. Or we can find all the indices where the array equals x. All of this can also be done using the same kind of algorithm. Next one is something about decision and optimization problems. So a lot of the problems are given some array, some input that includes x. Can you, for example, find an index where the array equals x, or some other one? And optimization problems are from what is the smallest, or maybe what's the largest x for which you can solve the same problem. You could, for example, ask, well, what is the largest x that occurs in my array? So optimization problems are typically harder than the corresponding decision problems, but often not by much. Because, well, actually some optimization problems, or many optimization problems, can just be reduced to the decision problem. Because if you ask what is the smallest x for which you can do something, then, well, basically, take all relevant values that x could take, and do binary search. So that's one way of solving this decision problem. It doesn't always work. You need some property of the code, and that's this monotonicity problem. So assume, for example, that x is an integer. Now we say that, so this decision problem that we solve, basically, whatever this discussion here is, so f of x will be 0 if this decision problem returns no, and 1 otherwise. Basically, can you find x in the array?
How do you do that in latex? Begin array C. Bracket and begin array C. Hmm? We found the math tools package. Or you can just use big in front of slash. Interesting. Let me try that. Oh, it works. That's pretty cool. Zero if a decision problem returns no. Okay. I remember this concept. Greater than or equal. Just be that. Oh, let's do that. It was just key. Right, I'll abstract it is all 0. Okay, I guess.
Is 0 x is going away and f of x is 1 over. So, in some such problems, we have a kind of monotonicity property, which means that f of x is always smaller or equal than f of x plus 1. And basically, if we look at the array that contains the values for x, or the values for f, so this is the first thing here with f0, and then the second entry will be f of 1, the third entry will be f of 2, etc. Until the last relevant value for x, maybe f of 10 is so, if this monotonicity property here holds, that means that, well, this array contains only zeros until it has 1, and then it only contains 1s. And now finding the smallest x, such that f of x is 2, is equivalent to finding the smallest index in this array that's equal to 1, so the array equals 1. And basically you can solve this problem by doing binary search over this array of the f values. And so now the overhead is a factor of order log cardinality of a, where a is the range of possible, the range of the relevant values for x. Okay.
What do you mean by
We call this discrete binary search when we solve optimization problems in this way based on decision problems. Okay, so we'll talk a little bit about sorting now. So how do we get this sorted array in the first place? Of course, if we have an array of n items or n integers, we can do a bunch of operations in constant time, which is reading the array as some index, writing into the array as an index, and comparing two items in the array. Okay, the question is now to design an efficient algorithm to sort the items. And so let's assume that, well, these are the only ways in which we can access objects in the array, or the only thing that we can do with objects in the array. So in particular, we cannot say, okay, access the array at index I, look at what's inside, and give me the fifth digit of this integer. We cannot go inside the object. The only thing we can do with the objects in the array is compare them. So either one is larger than the other, or they're equal value, or something like that. Okay, and that's why we're talking about comparison sort. So there's a few sorting mechanisms that always give us order and spare time, and probably you know that there's faster algorithms. You probably know that sorting can be done in order n log n time. One example to do this is merge sort that we already saw last time. Basically, if you have an array of size 1, there's nothing to do, it is already sorted. Otherwise, we take our array, divide it into 2, sort it to halves, recursively, by calling our algorithm again. And then now what's left to do is, well, merge these two arrays in a sorted fashion. We have two sorted arrays, we need to merge them into one sorted array. So that's the third step here. And we're thinking about this a little bit. It's easy to see that you can do this in linear time. But just simply maintaining indices to, well, the smallest values that you haven't processed yet, and increasing these indices, and producing a merge array. Okay. So what are the running times? Well, in the best case, this takes all n log n time, because we always divide the array into 2, and we always keep doing this until reaching arrays of size 1. In the worst case, also we take running time order n log n. It uses order n additional space. So if you're given some array and you're being asked to sort it, we need some additional space in order to basically create these subarrays that we will then merge later on. It would be nice to have sorting algorithms that don't use this additional space. But this is a reliable algorithm, it's fast, the space requirement is a little bit of drawback, and it's often useful. Okay, another way that you can obtain an n-log-n algorithm is by using heaps. So we saw that heaps are useful for priority queues. You have the top element that's always on top in a max heap, so then you can use a min heap, the smallest element is always on the top. So if we remember, so building a heap can be done in order n time, and then deleting, for max heap we delete the maximum value. Now we have min heap where we'll delete the minimum value, and this takes order log n time. So basically we build our heap and then delete the smallest value, put it into our sorted array, and then continue in the same fashion. And in the end, our heap will be empty, our sorted array will have all the values. Okay, so the correctness is obvious because we always remove the smallest element from the heap and put it into our sorted array. Again, the running times in the best case n log n, in the worst case also n log n, and so what's the additional space? Yeah, we also need some additional space for a heap. So this is again a quite nice algorithm. It says there's no additional space required. Yeah, so if you take the build function and just apply it to our array that's initially there, then yeah, it's true that you can do this without additional space. Okay. It has larger constant factors than the other sorts, so it's used less often in practice. But in theory, this is a very good sort. In practice, quicksort is very popular. Here, we need to designate one of the entries of the array as a pivot, and then basically what we're doing is, well,
what do you
put everything
mean? You
that
can't just
is
say
lower than the
that.
pivot in front of the array, then the pivot, and then everything that's larger than the pivot. And once we've done this, then now we need to sort everything in front of the pivot recursively, and everything after the pivot also recursively. Ideally, the pivot that we selected was the median of all our values, so it ends up right in the middle. But maybe we get unlucky and the pivot is maybe at the very front. So let's say we select some entry as a pivot, and it happens to be the smallest element of the array. Then, well, what we need to sort in our next recursive call is everything except one element. And that's very expensive to do if we keep doing this. So actually, in the worst case, the running time will be all n squared. So in the worst case, the pivot is always the minimum or maximum. So one of the subarrays is empty, and the other one has all the remaining elements. In the best case, if the pivot is right in the middle, it's a median value, then the running time analysis is like the running time analysis for merge sort, and so it's order n log n. The worst case is very rare, maybe except if you take a sorted array and take your pivot always at the first element of the array. In that case, well, sorting a sorted array would be very slow. Maybe that's better way to select a pivot where you're guaranteed that, well, if you actually take a sorted array, it will not take too much time. So that's the average case running time is order n log n. This is true depending on what our pivot is. If we actually manage to always find the smallest element as our pivot, let's say a pivot selection strategy that sets your way, finds the smallest element and uses that on the pivot, then well, it's still be an n-squared algorithm, even in the average case. If you take just the first element, probably the average case is so you see that, well, it's important how we select our pivot. We could select an element at random. This is a good strategy. We have very low chance of being in the worst case. We could do something smarter like the median of 3, like you take 3 elements, maybe one towards the beginning, one towards the middle, one towards the end, take the median of 3. So you perform well even if your array is 1, for example. You could take the median of medians. We'll say more about this next week. So merge sort is, for example, a good algorithm to use in this course. Since we don't care too much about constant factors, we don't care too much about the space, additional space usage. Merge sort is a nice algorithm. Quick sort is not used in practice because the worst case running time is order squared for quick sort. But encountering this running time is very rare. The also quick sort is the basis of sorting in many libraries in various programming languages. Okay, so there are a bunch of algorithms that do achieve order and running times. We don't care too much about the extra space used by merge sort or the larger constant factor of each sort. So if you consider the worst case performance, we will say that quick sorts order n squared running time is slow compared to these fast algorithms. So when you want to sort an array in this course, you can just say sort the array using merge sort or using heap sort. You don't have to describe those algorithms. Just assume that this can be done in order and over time. And the other algorithms are useful to understand conceptually and occasionally have some practical applications, especially quick ones. So the big notation hides constant factors, right? So that's something we know. For some of these algorithms, the constant factor might be larger than for others. And in practice, the constant factors do do make a difference, especially for something basic like sorting that we might use over and over again. So we actually do care about constant factor. But to actually know the constant factor precisely, you have to, first of all, decide, how much time does each of the basic operations take, right? So it's not that easy to give an answer. But that's why this is quite bad, right? Constant factor is larger than for all of our sorts. And it's actually difficult to be more precise. You can get a feeling for this if you implement the algorithms and just see that one of them is always slower than the other one, and it seems to be by a constant factor. You could. There's a book by Donald Knuth who has actually investigated this in much more detail. But he also had to fix, first of all, what operations are allowed to be used, how much time did they take, etc. So you could investigate this in much more detail. But, so in this course, we're not going to be more precise. So, can we do something faster than this? Well, the answer is no, at least not in the comparison sort mode. So if all we can do is take two objects and compare them to see whether one should come earlier than the other one, then no, we can't do anything faster. So in this model we can actually prove this. In general it's very hard to prove that something cannot be done. So that's why we need to restrict ourselves to this comparison sort model, and then we can actually prove that omega of n log n comparisons are necessary. So the gist is this. So let's say we have an array of objects, and all we can do is compare them, and we have n objects. So if we know nothing about these objects and all we can do is compare them, if we need to come up with a sorted array, then all the permutations are plausible, right? So all the permutations of these objects could somehow arise. Well, you cannot look at the values, all we can do is compare them to each other. So how do we do a comparison? Well, we take two of these objects and see is the first one larger than the second one, or is the first one smaller than the second one. So basically, we can compare two objects, and we can view this as like a decision tree. Like we can take object number 3 and compare it against object number, let's say 5. And then, well, either it's the case that A3 is smaller than A5. Let's assume that they have all distinct values, so we don't need to care about equality. Or it's the case that A3 is larger than A5. But these are the two possibilities, right? And then our algorithm, we don't know exactly how it works, because we must prove something about every algorithm needs to take at least this much time. So we cannot fix anything about how the algorithm works. We just know it does comparison. Right? So it might take some other two objects, A1 compared to A7, and then either A1 is smaller than A7 or the other way around. And so we said that all the permutations are plausible. So basically, at the leaves of the tree, we must have all possible permutations of the array. So we have n objects here. How many permutations are there? There's n factorial permutations. And this is a binary tree. We can view it actually as kind of a binary search tree where we search for this the correct permutation. And what's the height? Well, in order to actually get to n factorial many leaves, the height must be at least log of n factorial. What is log of n factorial? Well, it can be shown that so in this course we are not going to be more precise. So can we do sorting faster than this? Well, the answer is no, at least not in the comparison sort mode. So if all we can do is take two objects and compare them to see whether one should come earlier than the other one, then no, we can't do anything faster. So in this model we can actually prove this. In general it's very hard to prove that something cannot be done. So that's why we need to restrict ourselves to this comparison sort model, and then we can actually prove that omega of n log n comparisons are necessary. So the gist is this. So let's say we have an array of objects, and all we can do is compare them, and we have n objects. So if we know nothing about these objects and all we can do is compare them, if we need to come up with a sorted array, then all the permutations are plausible. Right? So all the permutations of these objects could somehow arise. If, well, you cannot look at these the values, all we can do is compare them to each other. Right? So how do we do a comparison? Well, we take two of these objects and see is the first one larger than the second one, or is the first one smaller than the second one. So basically, we can compare two objects, and we can view this as like a decision tree. Like we can take object number 3 and compare it against object number, let's say 5. And then, well, either it's the case that, well, A3 is smaller than A5. Let's assume that they have all distinct values, so we don't need to care about equality. Or it's the case that A3 is larger than A5. So these are the two possibilities, right? And then our algorithm, we don't know exactly how it works, because, well, we must prove something about every algorithm needs to take at least this much time. So we cannot fix anything about how the algorithm works. We just know it does comparisons. Right? So it might take some other two objects, A1 compared to A7, and then, well, either A1 is smaller than A7 or the other way. And so we said that, well, all the permutations are plausible. So basically, at the leaves of this tree, we must have all possible permutations of the array. So we have n objects here. How many permutations are there? There's n factorial permutations.
What is this guy yapping about?
And this is binary tree. You can do it actually as a kind of binary search tree where we search for this the correct permutation. And what's the height? Well, in order to actually get to n factorial many leaves, the height must be at least log of n factorial. What is log of n factorial? Well, it can be shown that log of n factorial, well, it's at most, well, no, it's not sufficient to provide lower bound. We need to provide we need to show that this is at least something, right? Can show that this is at least, let's say, in the n factorial, we have, well, n factorial is equal to n times n minus 1 times n minus 2, etc. So let's only concentrate on the big numbers that get multiplied. Well, and all these numbers are at least n half, and there's n half of them, right? So focus on the n half numbers, they get multiplied with each other. All of them are at least n half. Okay, so this is at least, well, we saw this log rule, right? We have something with this exponent here that basically can be taken out and put in front of the log. And then if we ignore constant factors, then we see that, well, this is omega and So I just specify this binary tree. The proof on the slides is slightly different, but it also uses the fact that n factorial is at least n half to the power n half. And so what do we have now? So basically, what does our sorting algorithm do? It takes a walk through this binary tree. So it does a comparison, finds something out, then does the next comparison, etc. And then in the end, it arrives at one leaf. How many steps did it take to arrive at this leaf? That's exactly the height of this tree, of this decision tree. And the height of the decision tree we saw is omega n log n. Okay, so we can conclude that the running time of our comparison sort algorithm, no matter how it looks like, is omega n log n. So this means that merge sort and heap sort are asymptotically optimal, and that's all we are going to say about comparison sorts. There are other kinds of sorts that we are going to see next time. Okay, see you next week. And
what the frick? Bird started yapping. Form a number of comparisons k such that 2 to the power of k is greater than or equal to at least n log n comparisons in the worst case. N factorial permutation in the worst case, only one of these is correct. Is the correct sorted order? This is an algorithm which performs k comparison, can get 2k different. Performs k comparison, can get 2 to the power of k different combinations of results from these comparisons, and therefore can distinguish between at most 2k permutations. What the frick?
Hello everyone there, this is Kevin Kumar. Today I am going to give you one important result about comparison based sorting algorithms. Any comparison based sorting algorithm in the worst case takes omega of n log n time or omega of n log n comparisons. That means whatever the algorithm you design in the future too, like even God designs a best algorithm for sorting, especially comparison based sorting, then that sorting takes minimum n log n time in the worst scenario or worst case. Why? We'll see. Before that, I want to tell you what is comparison based sorting algorithm. Comparison based sorting algorithm is a sorting algorithm which takes decisions or which orders the elements based on the comparison of elements. Like it compares the elements completely, based on that it decides. There are some algorithms which are non-comparison based algorithms. Example, radix sort. So radix sort takes elements like 123, 234. It compares the digits, right? It takes least significant digit and it compares. Based on that, it moves the objects. Okay. Then here you are not comparing the objects. We are comparing the digits inside it, right? So they are not comparison based sorting algorithms. Really, comparison based sorting algorithm always compares object versus object, not digit versus digit. You understand that? Then now such comparison based algorithms take minimum n log n time in the worst case. Why? Because the number of comparisons in the worst case are at least n log n. Why? We'll take best algorithm possible and we prove it. Let's say we have God's algorithm. Okay. So for sorting. So this is the best algorithm possible in the world, God's algorithm. Even that God's algorithm cannot do better than n log n. That means it can't do in less time than n log n. Why? We'll see. Let's say God's algorithm also should take the decision based on the comparisons, right? Let's say this God's algorithm is comparing some two objects first, right? O1 comma O2. Okay. Now I am assuming that I have an objects like this O1, O2, O3, so on, On. Before going to the algorithm, we see how many permutations possible for this n objects. We know that there are n factorial permutations. What I want to say is, if you give input O1, O2, O3 to your God's algorithm, then that God's algorithm is going to decide the right order. But right order is either O1, O2, O3, no one knows it. Based on the algorithm or based on the decisions, it will decide finally, right? Maybe O2, O1, O3, let me systematically write them. O1, O2, O3, maybe O1, O3, O2. Otherwise O2, O1, O3, maybe O2, O3, O1, O3, O1, O2, then O3, O2, O1. Yeah. Now your sorting algorithm is going to decide the right output, but no one knows the right output. So the right output is one of these 6 permutations. Okay. In general case, if there are n objects, the number of permutations are n factorial, isn't it? Now out of these n factorial permutations, one of them is the right output, but no one knows what is the right output before running the algorithm. Now your God's algorithm is going to decide the right output among that n factorial with some time complexity, with some comparisons. Okay. Now I am going to prove that God's algorithm should take a minimum n log n comparisons to decide the output. Why? We will see that. Now let's come to such algorithm. Let's say this God's algorithm is going to sort the elements, right? So maybe first time it compares two random elements O1 comma O2, right? After comparing O1 O2, then the outcome possibly O1 greater than O2, otherwise O1 less than O2. My small assumption here is all these objects are distinct, like all are different objects. Not a problem, right? If I take all are distinct. If all the objects are distinct, then if O1 greater than O2, your algorithm is going to take an action, number 1. If O1 less than O2, then your algorithm is going to take action 2. What is that action 1 or action 2? It depends on the algorithm. Finally, that algorithm actions may be moving the elements, right? After that, continuing the process. Right. So this action 1 is nothing but doing the remaining work, like sorting the other elements. Maybe action 2 is nothing but a different plan, like how to sort the elements. All these actions should lead to one of the sorted order, right? Okay. Now in this action number 1, probably immediately you will be comparing two more objects, like maybe O2, O3, any random. Now here maybe you are comparing O3 and O4, some two random elements. After comparing O2, O3, then there are two different actions possible. One is, if O2 greater than O3, you do something. O2 less than O3, probably you do something. Similarly here, based on O3, O4, you take two different decisions. What I want to say is, in that way, any algorithm, whatever you write, I can represent your algorithm like a decision tree. Right? So based on comparison of O1, O2, you are taking the decision. You are either coming this side or this side. If you come this side, you may compare two other elements. I don't know what are they. Depends on your algorithm. Finally, one day, you will reach to a point where, this is the last one, like maybe the last comparison. Maybe O1 comma On, I don't know, any two random. So after comparing these two, you decided that the right order is maybe O1, O2, something, some order. Otherwise, you may take another choice like O2, O1, something in that way. Finally, what I want to say is, by continuing this process, you will reach to a point where you get the sorted order, right? That is what the goal of any sorting order. But now, either this is the right order or this is the right order, this is the right order, it will be decided by your action plan. So what kind of control you took? Understand? For example, every time O1 greater than O2, after that if you come here, if you come here, then this is the order. In that way you decide, right? This is the illustration of any sorting algorithm. Now one important point I want to tell you, because there are n factorial possible permutations, we know that. Okay, then your output could be anything. Then I want to say that, so these leaves are nothing but outputs, but your output can be anything. Then these leaves are all possible n factorial permutations, isn't it so? Yes. Now your GOTS algorithm or any algorithm is going to take the right output based on the action plan like this. Right? If you understand this, you can understand the proof. Now, before going to this proof, I want to ask some questions about this tree. This is a binary tree, isn't it? Yes. Now we are going to find out the worst case comparisons, right? In the worst case, how many comparisons? Let's assume that this tree, because your algorithm is the best algorithm, so that this tree, you made this tree such a way that it is fully balanced. Why I am taking fully balanced, I will tell you. Okay, you have designed your algorithm such a way that that algorithm is creating a tree, just our imagination, but it's fully balanced. Then some students ask why. Then I say, if it is not fully balanced, then the other possible structure is this kind of narrow tree. If your algorithm gets this narrow tree, probably you see every node is about comparison, right? Comparison. At every node you are doing comparison. If you form this kind of lengthy tree, then there are a lot of comparisons, right? Then that may not be the best algorithm. If your algorithm is God's algorithm, then that algorithm should not take lot of comparisons, right? It should take as less comparisons as possible. To have as less comparisons as possible, the tree structure should not be like this. Then definitely it should be like this. Let me assume now my tree is like this. Now one fundamental question is, in this kind of tree, if number of leaves are k, you remember, then other nodes also will become approximately k. Okay, then total number of nodes will become 2k. And one more thing, the height of this kind of tree is log of total number of nodes, 2k. So log 2k is asymptotically log k. There is no much difference. Log 2k and log k are same. Now come to this. Then what is the height of this tree? The height of this tree is log of, because this tree is nothing but this one, log of k. K is nothing but number of leaves. Number of leaves in this tree is log of n factorial, where each leaf is one of the possible permutation of n objects. So log n factorial is nothing but n log n. Okay. How this n log n is related to our lower bound, I will tell you. Now, if this is your algorithms running behavior or flow, then in the worst case, what happens? The number of comparisons we have to calculate, right? See, one comparison here, then in the next level one more comparison, in the next level one more comparison. But we know that the number of levels or height of the tree is n log n. Then in the worst case, so you have to go through one lengthy path, and that lengthy path is nothing but height of the tree. Then I want to say that the number of comparisons are height of the tree, because height and number of comparisons are same, right? In every level you are doing one comparison. Then if your tree height is n log n, then that many comparisons sometimes you should do, right? So maybe sometimes you can escape some of the comparisons, right? But not always, correct? So in some point of time, that means in some cases, maybe you have to go through a lengthier path, correct? Lengthiest path, that is the height of the tree. When you go in this lengthiest path, why? In the worst case anything can happen. Then if you go through that path, then it takes n log n comparison. See, 1, 2, 3. For every level one comparison. So that's why. So your algorithm, though it is God sorting algorithm, takes n log n comparisons sometimes. That means lower bound for any comparison based algorithm is n log n. That's why it is omega of n log n. No one can do better than this.
Yeah, I gotta get it. others listed sorting algorithms are. The permutations or combinations? Performs k comparisons can get 2k different combinations of results from the something. What is 2 to the power k? What the heck? So n factor is greater than Alexa. Alexa, stop. Base 2 track and both 2. Yeah, I have no idea where they got that from. I ain't gonna lie to you. Is it log? Bruh. I think I kind of get it. Whatever, it is time to go to sleep.